Okay, so let's start. So this is good evening, Ajay. Yeah, so this is the eighth problem solving session that I'm conducting, and as usual, today we'll first solve some problems from the week eight's assignment as well as from content related to week eight, and then then towards the end we'll solve some problems related to week nine. Okay, so let's start. So the first problem from week eight's assignment is the following. Select the correct options. Option A is composition of a CPA secure encryption scheme with an SCMA secure MAC will always yield an authenticated encryption scheme. Option B is if message M is made up of blocks M1 to MD and a MAC is used to generate tags T1 to TD, then it is easy to forge a tag by reordering the messages. Option C is using separate keys for encryption and authentication is not needed if the correct order of encryption and authentication is used to obtain an authenticated encryption scheme. And option D is padding oracle attack is based on the error message sent by the receiver. So these questions are from the assignment, so you might have solved them. So if you know the answer and you would like to answer the question, you can answer in the chat. Okay, so let's move on this option by option. The first option is composition of a CPA secure encryption scheme with an SCMA secure MAC will always yield an authenticated encryption scheme. Well, this is false because we saw that there are three ways of combining a CPA secure encryption scheme with an SCMA secure MAC, and these three were authenticate then encrypt, encrypt then authenticate, and encrypt and authenticate. And we saw that only one of these, namely encrypt then authenticate, was the only one that was giving us an authenticated encryption scheme. So A is false. What about B? If M is made up of blocks M1 to MD and a MAC is used to generate the tags T1 to TD, then it is easy to forge a tag by reordering the message blocks. Okay, so this is true. And here's why. Okay, yeah, so B is true. And yeah, okay, so first let's go over all the options and then I'll tell you why B is true. So C is using separate keys for encryption and authentication is not needed if the correct order of encryption and authentication is used to. Yeah, so let me go over options C and D as well, and then I'll show you how we can do it. So using separate keys for encryption and decrypt and authentication is not needed if the correct order of encryption and authentication is used to obtain an authenticated encryption scheme. Well, this is false because we saw that even for the encrypt then authenticate uh, paradigm to obtain an authenticated encryption scheme, we still needed different keys for the CPA secure encryption scheme and the CMA or SCMA secure MAC. So C is false. And what about D? So D is padding oracle attack is based on the error message sent by the receiver. Well, this is true because recall that in the padding oracle message, the adversary was uh, cleverly altering the last block of the message, or rather the last block of the ciphertext, and in the hopes of finding out first the length of the padding and second the last bit of the message, the last byte of the message, right? And the way the adversary was able to do that was when it sent the modified ciphertext block to the receiver would in some cases send the message invalid padding or would send the message invalid padding back to the sender. And the adversary would intercept this message, and based on this, the adversary was able to find out both the length of the padding as well as the last byte of the message. So yeah, option D is also true. So now let's see how if a message is divided into multiple blocks and we use uh, Mac to generate tags for them independently, then it's easy to forge a tag by reordering the message blocks. So we'll, uh, show that this scheme can be broken, we'll just construct an adversary for this scheme. So we have the verifier and an adversary. And as usual, the goal of the adversary is to break this like uh, Mac scheme. So the verifier first takes a key uniformly at random from the key space. And what the adversary does is the following. The adversary sends the message where M1 to MD are the blocks of the message, and the verifier would compute the tag okay, and send T1 TD to the adversary. Now, here the message M sent by the adversary is not arbitrary. In particular, it has this constraint M1 not equals to M2. So after receiving these tags, what the adversary does is the following. It sends this message tag pair to the verifier, and over here the message is and T star is T2, T1 to T2. Now clearly, since the blocks M1 and M2 are different, M star is not the same as M, right? Yeah, since the messages M star and M are not the same, M star comma T star is a valid forgery. So by just reordering the message blocks, we can uh, forge reordering the message as well as the tags. We can forge a tag for a new message. Is this fine? Yeah. Okay, so if this is fine, let's move on to the next problem. So the next problem is which of the following is or are correct for the key exchange problem? Option A is the goal of the sender and receiver is to agree upon a common random key or a public channel. Option B is strong privacy for a key exchange protocol requires the adversary to be unable to distinguish the output key from a random element of the key space except with a negligible probability. Option C is the goal of the sender and receiver is to agree upon a common key or a public channel. And option D is weaker privacy for a key exchange protocol requires the adversary to be unable to compute the key except the negligible probability. So which of these are correct? Okay, so let's go over all the options. Option A is the goal of the sender and the receiver is to agree upon a common random key or a public channel. Yes, yeah. A, B, and D are correct. Yeah. Yeah. So Yes, this is indeed the goal of the key exchange problem. The sender and the receiver want to agree upon a common random key, but they don't have a secure channel to do it. Option B is strong privacy for a key exchange protocol requires the adversary to be unable to distinguish the output key from a random element of the key space, except with an negligible probability. This is also true. This is exactly the definition of strong privacy or strong secrecy or strong security. Option C is the goal of the sender and the receiver is to agree upon a common key or a public channel. Well, this is not completely true because they don't just want to agree upon a common key. They want to agree upon a common random key, right? Because if the key weren't random, then that can give the adversary who wants to break the crypto system some advantage, right? For example, let's say if the key is always zero to the end, that's a problem. So the key has to be random. So C is not correct. And D is weaker privacy for a key exchange protocol requires the adversary to be unable to compute the key except with a negligible probability. This is also true. This is just a definition of the weak privacy notion for key exchange protocols. So A, B, and D are correct. Is this fine? Okay. So let's move on to the next problem. Problem 3 is let the sender and the receiver have a pre-shared random and private AES key K. Then consider the following method of authenticating messages of size which are a multiple of 64. So we can think of our message as being blocks, divided into multiple blocks, and the length of each block is 64 bits. Okay. So to authenticate M in 0, comma 1 to the 64 less than equals to L with blocks M1 to ML, the tag generation algorithm outputs T equals to T1 to TL, where Ti is AES uh, is the encryption of MI concatenated with the binary value of L, the 64-bit binary value of L, and this whole thing is encrypted using key K using the AES algorithm. The tag, and this is the tag. This is how we generate the tag. The tag verification algorithm performs the appropriate verification steps. Now identify the correct options. Option A is the above MAC is randomized and hence SCM is secure. Option B is the above MAC is deterministic and hence is CMA secure. Option C is the above MAC is neither CMA nor SCMA secure. Option D is the above MAC when used with the encrypt and authenticate approach leads to an authenticated encryption scheme, and the adversary can always win this MAC forgery game. So which of these are correct? Okay, so let's go over all the options. So option A is the above MAC is randomized and hence is SCMA secure. Well, the MAC is not even randomized. So yeah, option A is incorrect. Option B is the above MAC is deterministic and hence is CMA secure. MAC is certainly deterministic, but whether it's CMA secure or not, that remains to be seen. In fact, what will show is that option C is correct. MAC is neither CMA secure nor SCMA secure. And let's see why. In fact, what we can do is something very similar to what we did in the previous problem. So we have a verifier and an adversary. The verifier picks a key uniformly at random. In this case, from 1 to the n, over here, n is 64. Sorry, 128. Yeah, it's 128. Yeah, like as well. The verifier picks a key uniformly at random from 0, 1 to the n. And what the adversary does is the following. Again, the adversary sends the message such that M1 is not equals to M2. The verifier sends the tag, and for all I t is equal to ti. Now, what the adversary does is the following. Here's how it produces a forgery, where m star is just as in the previous question, it's this, and t star is again similar. Sorry, t star 2. Oh no, it's p2. T1, Tn. Now, just yeah, again, like in the first question, a t star is a valid tag for m star because, uh, okay, what is ti? Ti is just AES-K of mi concatenated with L, right? Now, so T2 is the sort of the valid tag for M2, T1 is the valid tag for M1, and the same is true for every other Ti, right? So T star is a valid tag for M star. Also, M star is not equals to M because M1 and M2 are not the same, right? So M star comma T star is the valid forgery. Yeah, so there exists an efficient adversary that can forge a tag for a new message. So Mac is neither CMA secure nor SCMA secure. The above Mac, when used with the encrypt and authenticate approach, leads to an authenticated encryption scheme. Well, the Mac is not secure, so this is not going to happen. And option E is the adversary can always win the Mac forgery game. So we saw that the adversary can always win the Mac forgery game, right? We saw an adversary that can always win. So yeah, E is also correct. Is this fine? Okay, so let's move on to the next problem. So the next problem is select the correct options. Option A is a cyclic group has one or more generators. Option B is the group Z5, comma plus mod 5 has 5 generators. Option C is the group Z. Okay, let me use this multiplication. The group ZP cross with multiplication modulo P, where P is prime has prime order, and option D is 46 to the 51 mod 55 is 46. So which of these are correct? Okay, so let's go over this option by option. So a cyclic group has one or more generators. That's true. Yeah, A and D are correct. Yes. So cyclic group has one or more generators. That's how a cyclic group is defined. There must exist a group is cyclic if a generator exists, right? So A is true. Option B is the group Z5, comma plus mod 5 has 5 generators. Well, this is false because the group Z5 contains elements 0, 1, 2, 3, 8, and 4. So it has size 5. Now, we know that the identity element can never be a generator, right? So Z5, so this group can have at most four generators. Yeah, so it cannot have five generators. So B is false. Option C is the groups Z cross P comma mod Z cross P with multiplication mod P, where P is prime as prime ordered. Well, this is also not true because this group contains the elements 1 to P minus 1, right? So it has P minus 1 elements. And if P is prime, P minus 1 cannot be prime. Why? Because if P is 2, then P minus 1 is 1. That's not prime. And if P is any other prime, then P is an odd number. So P minus 1 is an even number. And then any even number other than 2 cannot be prime. So this is only true when T is 3. Otherwise, it is false. Yeah, so C is not true. And what about D? It says 46 with a 51 mod 55 is 46. So this is true. And okay, so let's see one way to solve this. There might be other ways, but yeah, let's see one way to solve this. Okay, so first of all, since we have mod 55 over here, and the operation is multiplication, the group that we are working with is this. Hmm, that is, the group operation is a multiplication mod 55, and the group contains all the elements which are co-prime to 55. Okay, so this is the group we are working with. Now here's one fact that will help us in solving this problem. The size of this set, or rather let me make it this. The Euler tuition phi n is the number of numbers in 1 to n minus 1 that are co-prime to. Yeah, so this is a, like this is a standard fact from member theory. Like, like have you seen this fact before? Yeah. So and so we now know that the size of Z55 cross is going to be 555. But what's 555? So here's another fact that will help us in calculating that. P and Q are primes. Times Q minus. Okay, so This fact gives us a way to compute the Euler torsion function when n is just a product of two primes. Now, why does this help? Uh, it's because of the following reason. 55 equals to 5 times 11 and 4. And size of, so this is 5 minus 1 times 40. Okay, so there are 40 elements in this group, right? Now, we also know this fact. G to the size of G is identical. So in this case, since we are working with a group of order 40, what we get is the following. 46 to the 51 is equal, forgot mod. So this is 46 to the 40 plus 11 mod 56, which is equal to 46 to the 40 times 46 to the 11 mod 56. And since we are working in a group with size 40, 46 to the 40 is going to be 1. So this is just, oh yeah, sorry, mod 55. Thanks. Yeah, so this is just 46 to the 11 mod 55. Yeah, so all we need to do is compute 46 to the 11 mod 55. And yeah, this takes some work, but yeah, we can do it. So I and 46 to the I mod 55. Right. Yeah, so when I is 1, it's just 46. Yeah, let me not draw these. I take too much time. When I is 2, it's 26. When I is 3, it's 41. When I is 4, it's 16. When I is 5, it's 21. When I is 6, it's 31. When I is 7, it's 51. When I is 8, this is 36. When I is 9, this is 6. When I is 10, this is 1. So when I is 11, we are going to get 46 again. So 46 to the 11 mod 55 is 46. And as we saw, that is the same as 46 to the 51, right? Yeah, so uh, D is also correct. Is this fine? By the way, suppose I want to compute, suppose I have 46 to the 4 mod 55. I want to compute 46 to the 5 mod 55. How would I do that? So what I'm asking is, how would you implement the mod operation? Let's fill a calculator.
टू पावर 4 में ही मल्टीप्लाई कर देंगे ना, जो मॉड करके आएगा।
Yeah.
एक्स
So
टू पावर
we
4 है, उसमें ही मल्टीप्लाई कर देंगे ना, जो मॉड करके आएगा, है ना।
right. Okay, so let's say we do four, we have 46 to the 4. So let us say we have 16, right? Now with 16, I would multiply 46, right?
यस।
So I would get 16 times 21, but that number is much larger than 55. So how would I compute that number mod 55? That's your calculator.
मल्टीप्लाई, आई विल मल्टी डिवाइड,
Right. Yeah, you are in the right track. Divide by what?
डिवाइड बाय मल्टीपल्स ऑफ 55, बट
Okay, there is a much more straightforward way of doing it. Divide by 55. Okay. Okay. So you are using a calculator. So it's going to be, so by default, it's going to give you decimal numbers, right? So divide by 55. What you would get is, let's say an integer point some number, right? Let's say you get x point y. X is an integer and y is everything after decimal point, right? So what you can do is subtract x from this and multiply 55. So if 16 times 46 is x point y, you subtract x, you get 0 point y, and you do 0 point y mod 55. This would give you a number that is very close to an integer. And yeah, it would give you something like, let's say in this case, it would give you, I think, something like 15.99997 or something like 16.00001. So you just take the closest integer. That's how you uh, like get 46 to the 5 mod 55 from 46 to the 4 mod 55. And if you are using a programming language, you can do this accurately, right? Because C allows you to do modular arithmetic. So this is fine. Yeah. So let's move to the next problem. So the next problem is, consider a PRF for a pseudo-random function fk from 0, comma 1 to the n to 0, comma 1 to the n. And using this pseudo-random function, we'll generate a keyed function f prime k from 0, comma 1 to the 2n to 0, comma 1 to the 2n as follows. So let us suppose that, oh, by the way, this should be f prime k, not fk. Yeah. So the keyed function f prime k would be considered as follows. Suppose we have an x which is x1 concatenated with x2, where x1 and x2 are both n-bit strings. Then f prime k is defined as f of k concatenated with f of k fk fk of x2. So this is how f prime k is defined. And the options are, f prime is a pseudo-random function, and when used directly leads to a CMA secure map. Option B is f prime is not a pseudo-random function. Option C is f prime is a pseudo-random function, but when used directly does not lead to a CMA secure map. And option D is f prime when used directly does not lead to a CMA secure map. So which of these are correct? Okay, so the correct options are B and D. And let's see why. So yeah. So we want to show that f prime is not a secure PRF. So what we're going to do is we're going to construct an efficient adversary that can distinguish between f prime and a random function. So we have a verifier and we have an adversary. So the verifier at the very beginning picks a bit from 0, comma 1, right? The adversary sends, okay, we'll just send two messages. Uh, oh wait, it's X, right? So we'll send two. So the adversary queries the function at 2 points, x1, x1 and x2. And let's say x11 is equal to x21 and x12 is not equals to x2. So the two messages are different, but the first block is the same. And what does the verifier do? If b is equal to 0, then the verifier just sends a random string. And if p is 1, then y is said to be f prime k of xi, x1 and sorry, y1. Yeah, this is y1. So it wants to answer to two queries, so it should pick two things uniformly at random. And send y1 and y2. And when b equals to 1, y1 is this and y2 is again f prime kx. And what the adversary does is the following. Let yi be yi1 concatenated with yi2 is it checks if sorry, if y11 equals to y12. If yes, it sets p prime to 1. If no, then it sets p prime to 0 and sends p prime to the verifier. So now let's look at this probability. So when b prime is 1, the verifier is using the keyed function f prime k, right? Now f prime k of x1 is just fk of x1 concatenated with fk of x2, and f prime k of x2 is f prime k of x21 concatenated with fk of xk of x22, right? But the thing is, since x11 and x12 are the same, this part of both the strings y1 and y2 is going to be the same, right? So in particular, this check will pass. So this probability is 1. On the other hand, this probability, okay, so when b is 0, y1 and y2 are random strings of length 2n. So what's the possibility that y11 equals to y12? Well, it's 1 over 2 to the n, because both y11 and y12 are n-bit random strings. So so fix any value of y11. The probability that y12 would also be the same value would be 1 over 2 to the n, right? So these are the two things, and therefore this is very large and it's so negligible. Uh, Yeah, so there exists an efficient adversary which can distinguish f prime from a totally random function. And so f prime is not a PRF. So option B is true. Okay, what about option A? Option A and option C both state that f prime is a PRF, so they are clearly wrong. So B is true implies A and C are wrong, and we are left with D. T states that F prime when used directly does not lead to a CMS secure MAC. Well, this is true because for a CMS secure MAC we need the function F prime to be a PRF, right? But it's not a PRF, so D is also true. It won't lead to a CMS secure MAC. This is fine. So now let's move on to the next problem. Okay, so the next
So
problem is
can you repeat third portion पार्ट सी मतलब जो आपने आंसर बताया.
oh, third question. This one?
यस सर इसका मतलब जो सी पार्ट क्यों आया था ट्रू वो एक बार ही दिखा दो एक बार.
Oh, the above MAC is neither CMA nor SCMA secure. Okay. So what is happening in this MAC? We have a message M, which is divided into blocks M1 to ML, right? And we are computing the tag like this. So we are basically computing the tag of each and every block individually, right? So here's what we can do. The adversary sends a message M1 to ML, but M1 and M2 are not the same, right? Now, the verifier would send these tags. Let's say the tags are T1 to TL, right? Now, even individually, M1 is the right tag for T1, sorry, T1 is the right tag for M1, T2 is the right tag for T2, M2, and so on, right? So when the adversary sends the message M star comma T star, where M star is M2, M1 up to ML, and T star is T2, T1. Oh, okay, yeah, maybe this is causing the confusion. I should write it like this. M2, M1, then M3 up to ML. So we are just reversing the first two blocks. Okay, so the adversary just sends these M star and T star to the verifier. Now I claim that T star is a valid tag for M star. Why? Because what is T2? T2 is AESK of M2 concatenated with L, which is fine. Same with T1, right? T1 is AESK of M1 concatenated with L, and same with T3 to TL, right? So T star is a valid tag for M star. Is this fine? Yeah. And M star is not, sorry, M star is not the same as M because of because M1 and M2 are not the same. So so the message M and M star differ in the first two blocks. So we have been able to generate a tag for a new message. So this is a valid forgery and this is not CMS secure nor SCMS secure. Yeah. So is this fine? So yeah, let's move on to this problem. This problem is how many generators does the group Zn uh, plus mod n have? So this is the group of all numbers from 0 to n minus 1 and the operation is addition mod n. So how many generators does this have? So would you like to take a guess? Okay, so let me tell you the answer. It is phi and many generators. Recall that phi n is the Euler-Torsson function, the number of uh, numbers in 1 to n minus 1 which are co-prime to n. Let's see why. So first, so do you know what an order of a group element is? Okay, yeah. Anyways, let me define it just to be safe.
लीस्ट पावर मतलब जो ऑपरेट करने के बाद आइडेंटिटी आएगा.
Right. In this case, it won't be a power. In this case, it would be a product, right? Yeah, so since the group is additive, it won't be a power, it would be a product, right? Because when I perform operation, when I perform the addition operation m times, I get m times g, right? So this is the order of an element in Zn. And oh wait, it's not zero, zero mod. Yeah, because all the operations are happening mod n, right? So m times z is zero mod n. Now here's the first claim. So let me denote this by small o of g. So if g is a generator of Zn, then the order of g is equal to the size of Zn. So have you seen this before? Or should I prove it? So we know that for any g in Zn, size of Zn times g is equal to 0 mod n. So the order of g is clearly less than or equal to size of Zn, right? Also, strictly less than Zn, size of Zn, then the group generated by is this, right? Yeah, I should write this subgroup is G 2G, 3G all the way to order G times G, I, and this is not equals to Zn as size of the set, rather, yeah. Okay, so this is the group generated by G. Now, size of this G is not a generator. So what we have shown is that the order of if the order of any G is at most the size of Zn, and if the order of G is less than the size of Zn, then G cannot be a generator. So this means that G is a generator if and only if the uh, order of G is equal to the size of Zn, right? In fact, the converse is also true. Yeah, so let me modify this statement. G is a generator of Zn if and only if. Yeah, so if G, so far what we have shown is that if the G, if G is a generator, then it's so far we have shown this direction, right? If G is a generator, then its order is size of Zn, and if uh, yeah, so now let's see the other direction. Wait, mhm. Do we need this? Yeah, okay. And the group generated.
Sir, is it not the definition of generator of of a group?
Okay, so okay, there are two ways to define a generator. The definition that I was using is the following: G is a generator if every element of the group is can be written as M times G. So like yeah, this okay.
Okay, okay, okay. Yeah.
Another way to define a generator is just say any element whose order is the size of the group. That's also true. So what I'm just doing is going to the first and the second definition. So if order of G is size of Z, then the group generated, then the subgroup generated. G is G is this G to G up to size of Z, and so the subgroup of G has size equal to Zn, and so the subgroup of G is exactly Zn. Yeah, so if order of G is equal to the size of Zn, then G has to generate Zn. So G is a generator of Zn if and only if the order of G is exactly Zn. So now let's use this claim to show that the this group has like exactly phi and many generators. So first thing. So now notice that phi n is the number of coprime numbers between 1 to n minus 1, right? So what we'll do is just the following. We'll show that every number which is coprime to n is a generator of Zn. Okay. So let G be coprime to n. Then uh, m then m times G is equal to 0 mod n implies okay implies that m times G equal to k times n for some k in n, right? Now since uh, n and G are coprime, that is that GCD is 1. That is G and n do not share any prime factors, right? So all the prime factors of n that appear in the RHS, since they must also appear in the since they appear in the RHS over here, they must also appear in the LHS over here, and so all the prime factors of n must divide m, right? So we get that n divides m. Okay. Okay. So there is one more thing. So, order of G is a multiple of n, which is equal to the size of Zn. However, we know that order of G is less than equals to n, right? So, order of G is exactly n, and from 1, G is a generator. Yeah, so we have shown that every, okay, yeah, let me write one more thing. Okay, so we have shown that every number which is co-prime to n is a generator of Zn, right? So and since the number of co-prime numbers is at least phi n, sorry, since the number of co-prime numbers is exactly phi n, the number of generators is at least phi n, right? So is this part fine? Yeah. So then let's look at the second. Let G be such that uh, let me call this L. That's device. Let me call this P. So now we'll look at the other case when where G is not co-prime to N. Okay, N. So in this case, let the GCD of G and N be D, and since they are not co-prime, D is going to be something other than 1. Then notice that G, and notice that um, no, wait, okay, okay, yeah. Then the LCM of, okay, then define, yeah, then let's define L to be the LCM of, do I need to define LCM? Okay, okay, maybe I can do this directly without defining the LCM, but yeah, just for the sake of simplicity, let me define LCM. So let L be the LCM of C and N. Then we know that the LCM of two numbers is this, right? Which in this case is N times G over D, strictly less than N times G, right? Because D is not one. Yes, so we have this. Now, notice that L times G, okay. So now notice that L over G times G is equal to 0 mod N. Why? Because first of all, L times G is an integer because L is the LCM of G and N. So both G and N divide N. So L times G is an integer and L times, sorry, L over G is an integer and L over G times G is just L. And since L is the LCM of G and N. N also divides L, right? So L is 0 mod N. Hence, also the order of G is less than or equals to L over G. In fact, it would be exactly this. Now, uh, we saw that L is okay. So over here we saw that L is strictly less than N times G, right? So this thing is strictly less than N times G over G is equal to N, is equal to size of Zn. So the order of G is strictly less than the size of Zn. So from mm, G cannot be a generator. Yeah. So since any number which is not co-prime cannot be a generator, the only numbers which can be generators are the co-prime numbers. So the number of generators is less than or equal to phi n. And in part one, we saw that the number of generators is at least phi n, right? So these two together give us that the number of generators is exactly phi n. Is this fine? Yeah. So now let's move on to the next problem. The next problem is the following statement true or false? Every cyclic group is abelian. Is this true or false? Yeah, right. Yeah, so this is true. The reason is the following. Uh, right, yeah, exactly. Yeah, because every element is comes from the cyclic group. And let me say that the size of G equals to 10. There exists an element G in G such that G is equal to 1 G square and so on up to G to the n minus 1, right? So I and G 0 to n minus 1. Hence, uh, A times B is equal to G to the I times G to the J. Yeah, and so the group is abelian. So now let's move on to the next problem. Let GL n comma R be the set of all n cross n invertible matrices over the field of real numbers. Okay, then select the correct option. Option A is GL n comma R with addition operation is a group. So over here by addition and multiplication, I mean matrix addition and matrix multiplication. Okay, Option D is GL n comma R with multiplication operation is a group. Option C is GL n comma R with a product operation is an abelian group. Option D is GL n comma R with product operation is a cyclic group. And option E is GL n comma R with plus and product operation is a field. So which of these are correct? So you're saying A and B are correct, right? Okay. B is correct, but A is not. So let's see why. The identity element. So what's the identity element for matrix addition? Yes, it's the all zeros matrix, right? Yeah, so it's the all zeros matrix. However, the all zeros matrix is not invertible. So it is not in. Yeah, so since the identity is not present, it's not a group.
It is also not closed, na?
Right, yeah. You can also do it like that. So option B is G. Yeah, so this is a group. So we need to verify four things, right? The first one is closure. So if both are invertible, then AB is also invertible, right? Hmm. Okay, so why is this true? Why is this true that if the product, if A and B are both invertible, then the product is also invertible?
Determinant will be non-zero, na? For
Right. So
because
yeah. So determinant of A times B is just determinant of A times determinant of B, and since A and B are not invertible, determinant of A is non-zero and determinant of B is also non-zero, right? So determinant of A times B would also be non-zero, and it would also be invertible. So closure is fine. What about associativity? Okay, we know that matrix multiplication is associative. Yeah, so this is also fine. What about identity? So when we are looking at the multiplication operation, the identity is the identity matrix, right? And I n cross n, because I n cross n times A is equal to A times plus n is equal to, and I n cross n is invertible. The fourth thing that we need to look at is inverse, right? So for any A in GLN, comma, well, A is an invertible matrix, so there exists A inverse such that A inverse times A is equal to A times A inverse is equal to IN. Also, uh, A inverse is equal to A, right? So A, okay, so there exists a matrix A inverse that the product of A and A inverse is identity. But now A inverse should also be in GLN, right? But it is because A inverse is itself invertible, as its inverse is just A. Yeah. So all four properties are satisfied. So B, the B is a group. What about C? Is this abelian group? Well, no, because we know that matrix multiplication is not commutative. So C is not true. What about D? Is this a cyclic group? It is also not a cyclic group because it is not an abelian group. And in the previous question, we saw that a group is cyclic only if it's abelian, right? So D is also not true. What about E? Well, for G, L, N, R with the matrix multiplication and matrix addition operations to be a field, it has to be an abelian group under the addition operation, right? But in option A, we saw that it is not even a group under the addition operation. So it cannot be a field. So yeah, this cannot be a field. Is this fine? Yeah. So let's move on to the next problem. So the next problem is the following. So we saw in class that encrypt and authenticate approach need not give us an authenticated encryption scheme, right? But what we'll see in this problem is that the encrypt and authenticate approach, when used with a secure PRF, then SCMA secure MAC, would always give us a scheme which provides ciphertext integrity. So recall that for a scheme to be authenticated encryption scheme, it has to have CCS security and it must provide ciphertext integrity. So in this problem, what we'll show is that uh, encrypt and authenticate approach, while it might not provide CCA security, does provide ciphertext integrity. Okay, so let's see how why this is true. So recall that in ciphertext integrity, uh, we want to show that there does not exist any adversary who can produce a ciphertext for a new message, right? So what we'll do is we'll do a reduction. So what we'll show is that if there exists an adversary which can forge a ciphertext for a new message, then the MAC cannot be SCMA secure. That would be a contradiction and we would be done. Okay. So let's okay, even before this. So let me call Oh yeah, so okay, so what integrity means is that you shouldn't be able to come up with a new message, right? And what authentication means is that the receiver should be able to verify that this message came from the sender. So there's a slight
Okay,
difference
okay.
between them. Yeah.
Okay.
Also, I need a CPA secure scheme, right? So yeah. Okay, so I'm using a PRFI side. Okay, so rather let me write it like that. This be a CPA secure scheme constructed using a secure PRF. Okay, okay. Okay, so there are two things. There is authentication and there is authenticated encryption. So authentication is what I just told you, but authenticated encryption is CCA plus ciphertext integrity. Is this fine? Okay. Yeah. So okay, so we have a CPA secure, we have a PRF, so we can consider a CPA secure scheme from it, right? So I would also need, yeah, I would also need to define part. I also need to say what pi is here. So that pi equals to gen tag generation tag parent. Okay, yeah. So this is what we have. Okay, so why did we not take CCA plus message authenticity in authenticated encryptions? So okay, so what you're asking is why did we define authenticated encryption scheme in a slightly different way?
Yes, yes.
Okay,
Why मतलब हमने ये क्यों नहीं लिया कि CCA प्लस ऑथेंटिकेटेड वो मैसेज मतलब
okay, so
ऑथेंट
okay, so the way we have defined it, it is sort of this as well. So okay, a CCA plus message ciphertext integrity also implies this definition that you are suggesting. Because if you cannot force the ciphertext, so if an adversary cannot force the ciphertext, then when a receiver receives the ciphertext, the receiver is sure that the ciphertext came from the intended sender, right?
यस यस हाँ मतलब इंटीग्रिटी और वो तो सेम ही लग रहा है पता नहीं
Okay, so okay, integrity and there is just one difference between integrity and authenticity, and it's this. In authenticity, you just want to verify that the message came from the sender, right? Integrity is that you shouldn't be able to force a message. So integrity implies authentication.
यस यस यस
Yeah. Okay, so where were we? Yeah, okay, yeah. So we have okay, so we have a CPS secure scheme, secure MAC, and what we'll do is we'll play two games. So one game, And over here, we'll play the ciphertext integrity key. Diversity and scheme pi prime. Okay. And what we'll do, what we'll show is that if A prime succeeds, then A succeeds in the MacForge key. So first of all, the verifier picks the key K2 from, yeah. Okay, so the verifier picks key K2 for the Mac, so it's Chen. And A picks key K1 from Zen prime, double prime. And what A does is, A is going to send a bunch of messages, right? And sorry, A prime would send a bunch of messages. A would just forward these to the verifier. What will the verifier do for all I in N? The verifier would compute Ti defined as and send these tags to A. Now, since okay, now what A will do is the following: it would compute using this gets encryption. Yeah, the C1 T1. Yeah, so we are using the encrypt and authenticate approach. So we are supposed to encrypt the message using one key and authenticate it using another key, right? And then just combine the ciphertext and tag and send it to the adversary A prime. Now, adversary A prime is an adversary of the ciphertext inforgeability game. So it's going to output a C star and T star. What A will do is just the following. It will send T star to the verifier. Okay. So now what we want is the following. When C star T star, or rather let me write it like this. So C star T star is a valid forgery, a new message. M1 to M1. So if C star is a valid forgery, C star comma T star is the valid forgery for a new message, then we are going to have that T star valid tag for a new message. Or I can copy it. Yeah. Okay, so is this fine? Whenever C star T star is a valid forgery, so what does that mean? C star can be obtained from M star by encrypting it, and T star can be obtained from M star by generating a tag, right? So when C star T star is a valid forgery for a new message M star, that means that T star is a valid tag for a new message M star, right? So probability that what's the ciphertext integrity? Oh, there should be N. So the probability that so okay, this is the first event and this is the second event, right? when the first event happens, then A prime wins its game, and the second event happens when A wins its game. So what we have is this because of this implication. So whenever A prime wins his game, A also wins their game, right? So probability that oh no, ciphertext integrity, hmm, A prime comma. Let's like this. So probability that A max forge. The probability that A succeeds in forging a Mac is at least the fact that pi is SCMC. Yeah, so since whenever A prime succeeds, A succeeds, the probability that A succeeds is at least the probability that A prime succeeds, right? And since we are uh, by assumption, we assume that A prime succeeded with a non-negligible probability, right? This should be non-negligible.
सर ये जो ग्रेटर देन
Yeah,
इक्वल टू लिखा है ये इसलिए लिखा है क्योंकि उसका स्पेस ज्यादा है मतलब साइबर टेक्स्ट भी है उसके साथ इस वजह से टैग वाले
okay.
में
So
केवल
the reason I've written this is oh,
और ग्रेटर देन इक्वल टू या
wait,
व्हाई इज
okay.
इट नॉट इक्वल टू मतलब
In this case, it might be equal to okay. So whenever you have one event implies another event, let's say event A implies event B, the probability that the probability that B happens is at least the probability that A happens, right? But in this case, I think this might be equality. Let me see. Okay, no. It might not be an equality because this can happen, right? So A prime. So consider the following situation: A prime sends C star T star, where C star is not the correct encryption for N star, but T star is somehow the valid tag for N star. Okay. So in this case, A prime fails because C star T star is not a valid ciphertext, right? However, T star is still a valid tag, right? So there is at least one case in which A prime fails but A succeeds. Okay. So the probability that uh, A succeeds is at least the probability that A prime succeeds, right? Need not be an equality. Is this fine? Yeah. Yeah. So the probability that A succeeds is at least the probability that A prime succeeds. But by assumption, we assume that A prime can crack ciphertext integrity. So this is non-negligible, but that is a contradiction because pi is SCMA secure, right? So this implies that the scheme pi prime has to be ciphertext integrity. Must provide ciphertext integrity. Is this fine? Yeah. Yes. In that case, let's move on to the next problem. Now let's look at problems based on weak times contents. So the first problem is which of the following elliptic curves is or are singular? The options are y square equals to x cube minus x. Option B is y square equals to x cube plus 10x plus 7. Option C is y square equals to x cube minus 3x plus 2. And option D is y square equals to x cube plus 2x plus 1. So would you like, so this needs to be worked out, but would you like to guess which of these are singular?
सर कंडीशन याद नहीं है वो ए और बी के
Okay,
बीच
okay,
में
okay.
जो
Okay, let me write it. Yeah. So the elliptic curve y square equals to x square plus a x cube. Singular if and only if 4a cube plus 27b square equals to 0. Okay. Okay. So like let me tell you the answer, then we can go over all four. Rather, let's just go over all four curves. So A. In option A is what? -1, B is 0, right? So 4a cube plus 27b square is equal to -4, which is non-zero. So A is not singular. What about B? A is 10, B is 7. So 4a cube plus 27b square is equal to 4 times 1000 plus 27 times 49. Okay, this is non-zero because all numbers are positive, so we don't need to calculate the exact value. In option C, A is -3, B is okay, what is this? 4 times -27 plus 27 times 4. So this is 0. So C is singular. And what about D? Okay, again, D can't be singular because both are positive. And 4 times 8 plus 1 is not equal. Yeah. So the only singular curve is C. Is this fine?
यस सर। सर ये इक्वेशन में कैसे आते हैं ये वाला इफ एंड ओनली ये कैसे प्रूव करते हैं 4a क्यूब
Oh, okay, okay, okay. So this is the definition of a singular curve. This is how a singular curve is defined. Okay, so okay, that is strictly speaking not true. This is how we define the singular curve in the class. Turns out when this condition is satisfied, you would get three distinct roots. So where is yeah. So this is a degree 3 thing, right? In X. So it can have at, at most three distinct roots in X, right? And it turns out that whenever this is satisfied, it would have three distinct roots. So we call a curve where you have three distinct roots a non-singular curve. Is this fine?
यस सर
Yeah.
एंड व्हाई आर वी यूजिंग द मतलब ये वाला नॉन सिंगुलर में ये क्यों काम कर रहे हैं क्योंकि ग्रुप बन जाता है वरना नहीं बनेगा ऐसा कुछ
Okay, so I'm not sure if you can define elliptic like groups over singular curves, but non-singular curves have some okay nice geometric properties. For example, like you have three distinct roots, so you cross the line three times. Like,
हाँ
basically, there are some
तो
nice
मेरे को
geometric
लगता
properties.
हाँ मेरे को लग रहा है ग्रुप नहीं बनेगा फिर वो ग्रुप का स्ट्रक्चर नहीं आ पाएगा वो जो बनाते हैं
Okay.
इलेक्ट्रिकल
Okay, so I'm not okay. So that okay, but what you're saying is that the structure that we saw in class might not give you a group, right? But it's possible. What I'm not sure about is the following: is there some other way to define a group on such singular curves, right? Let's say, for
यस
example, by defining addition operation some other way, right? That's what I'm not sure about.
ओके सर
Yeah. Okay. Yeah. So the next problem is that G be a prime order cyclic group with order Q and a generator G. Let H from G to script K be a hash function modeled as a random oracle. So what we are assuming over here is that is h from g to k is a random function, and every entity in our construction has Oracle access to it. Then which of the following problems should be difficult to solve in G so that when alpha and beta are picked uniformly at random from 0 to q minus 1, the tuple G alpha, G to the alpha, G to the beta, and h of G to the alpha beta is computationally indistinguishable from G to the alpha, G to the beta, R. And R is a random element of Q. And the options are discrete log, CDH, BDH. So, like, would you like to guess which problem should be difficult for these two to be indistinguishable? Or put other way, let's say,
All
which,
of the above. All.
okay, okay, so A and B are certainly true. Erase that. So A and B are certainly true. Why C? Okay, so if this H weren't there, then you would be right. C would also be true. But since H is there and we are modeling H as a random oracle, this is anyways completely random, right? So it doesn't matter whether you can distinguish G to the alpha beta from a random G to the gamma, right? Because both these
Okay, okay. So
are
advantage
going
will
to
be
be
zero, na? Matlab
right. So
negligible.
right, both of them would be like indistinguishable, right? So DDH won't help, but see, but yeah, okay, so DDH being easy might not help, but D-log and CDH being easy would help. So let's see why. Okay, so okay, so we know that D-log being hard implies CDH being is hard, right? So okay, what I'll show is if CDH is easy, then we can distinguish between these two, and that would also imply that if D-log is easy, we can distinguish between the two, right? Because whenever D-log is easy, CDH is easy. Okay, so let's first so if B is true, A must be true. Now let's look at B. Now suppose CDH is easy, then given G to the alpha, G to the beta, and H of G to the alpha beta, we can efficiently compute G to the alpha beta, right? Okay, wait. Yeah. Okay, so what we are given is something like this: G to the alpha, G to the beta, and Y. What we don't know is whether Y is H of G to the alpha beta or a random string, right? So given G to the alpha, G to the beta, and Y, we can efficiently compute G to the alpha beta. Then we can query H for H of then we can query a random oracle. H of G to the alpha beta and check if H of G to the alpha beta equals to Y, right? And so probability that H of G to the alpha beta is equal to Y Given that the tuple we are given is g to the alpha, g to the beta, h of g to the alpha beta, this probability is always going to be 1, right? And what about this probability? Okay, so this will be, wait, what is the domain here? Domain is k, right? This is 1 over size of k. So we'll say distinguishing the two with probability 1 minus 1 over size of k. Rather, it's non-negligible. Yeah, so if we can solve CDH, then we can easily distinguish between the two scenarios. So CDH must be hard, and therefore D log must be hard. Is this fine?
Yes, sir.
Yeah. Because the 12th problem is we want to build a pseudo-random generator or PRG from ZQ square, that is from ZQ cross ZQ to G cube, where G cube, uh, where G is a prime order cyclic group of order Q with a generator G. And in this group, D log, CDH, and DDH assumptions hold. Okay, then let f of alpha comma beta be defined as g to the alpha, g to the beta, and x. So for what values of x, the function is not a PRG. Options are g to the alpha plus beta. Option B is g to the alpha. Option C is g to the beta, and option D is g to the beta. So for which of these values of x would this not be a PRG? Okay, so oh, yeah. So for these three values, it won't be a PRG. Why? Because let's look at A. Given G to the alpha plus beta efficient, and then compare it with X. And okay, I'm not doing the exact probability analysis, but if we are dealing with a pseudo-random string, then with probability 1, X would be G to the alpha plus beta. And if you are doing with a random string, yeah, this won't happen with a large probability, right? So we can distinguish between the two. About B, uh, we can compare G to the alpha and X. For D, we can compare G to the beta and X. And what about C? Well, in C, we have G to the alpha, G to the beta, G to the alpha beta, which is computationally indistinguishable from a random g to the alpha, g to the beta, and g to the gamma, right? So in when we use A, B, and C, we won't get a PRG, but when we use C, we can get a PRG because of the DDH assumption. Is this fine? Okay, so yeah, if this is fine, let's move on to the next problem. So the next problem is choose the correct combination. Okay, so by the way, before I begin, over here, when I say D log implies DDH, what I mean is that D log assumption implies the DDH assumption. Okay, that is, if D log is hard, then DDH is hard. That's what I mean by these. Okay, so we are supposed to choose the correct combination, and on the left hand side we have D log implies DDH, DDH implies CDH, CDH implies D log, and CDH implies DDH. And on the right side we have true, false, and no. We don't have. So like, what's the correct combination? What would one map to?
Is it not depend on the group? मतलब,
Okay, no, no, so that's what I'm saying. Suppose we have a group, okay, and suppose that in that group, okay, so let's look at the first thing over here. Suppose we have a group G, and what I'm saying is, no matter what G is, does D log assumption always imply the DDH assumption? Is it fine now? Is it fine now? So basically, what I'm saying is, no matter what the group is, does D log implies DDH? DDH in option one. Sorry. Okay. Yeah. So what should one map to? Does D log imply DDH? So is it true that if D log is hard, DDH is also hard? Okay. What do we know? We know that if uh, D, D log is easy, then CDH is easy, and if CDH is easy, then DDH is easy, right? But what we don't know is uh, okay. Yeah, let me write it. For one. So for one, we know that there exist groups for which DDH does not hold, but CDH holds, and since CDH holds, D log holds. So one is not true. What about two? DDH implies CDH. Okay, so if CDH is easy, implies DDH is easy. So the contrapositive would be if DDH is hard, then CDH is hard. So this is true. What about third one? CDH implies D log. So we know that if D log is easy, then CDH is easy. The contrapositive would be if CDH is hard, then D log must also be hard, right? Yeah, and four. So we know that if CDH is easy, then DDH is easy. But with wait, yeah, yeah. So we know that CDH is easy. Okay, yeah, it's the same as 1. Yeah. So we know that there exist groups where CDH is hard, but DDH is not hard. So CDH does not imply DDH. So 4 is also false. So 1 and 4 are false, 2 and 3 are true, and yeah, nothing, no, nothing is known doesn't come up at all. Is this fine? Yeah, let's look at the next one. Yeah, so again, it's choose the most appropriate combination. On the left hand side, we have groups. On the right hand side, we have assumptions. So the first group is ZP with addition mod P. The second group, oh wait, I should write P is prime. Yeah. So the left hand side, we have ZP with addition mod P where P is prime. ZP with multiplication mod P when P is prime and elliptic curve groups. And on the right side, we have D-log assumption. We have that D-log is believed to be hard, TDH is believed to be hard, and CDH is easy. So what does one map to? So for one, we know that D-log is easy. Uh, in ZP plus P, right? And D-log is easy, implies CDH is easy. So one maps to C. What about two? So we know that in two, D-log is believed to be hard, but DDH is believed to be easy. Yeah, so it can't map to two, so it should map to A. And in elliptic curve groups, we know that all three. D-log, DDH, CDH, let's put CDH first. Yes, that uses this. Is this fine? Yeah. Then let's move on to the next problem. So we stated this in class, we'll prove it over here. So let P and Q be primes, so that P is equal to R times Q plus 1 for some natural number R. Then prove that the group G, defined as H to the R, where H is in ZP cross, has size exactly Q. So this was stated in class, we'll prove it over here, okay? So yeah, let's prove it. Z cross this mod P is a cyclic group. This we saw in class, right? So let G be its generator. Now, Okay, so order of G is exactly equals to size of ZP cross. That's P minus 1, right? So let me write like this. These are distinct. So why are these distinct? Because the order of G is P minus 1 and QR is P minus 1, right? So all of these are distinct and contained in the group G, right? Okay, so is this fine why they are contained in G? It's because pick anything over here, pick anything over here. It has the form G, uh, G to the I R, right? And so it's the RF power of G to the I. Okay, so this all of these are distinct and are contained in G. So the size of G is, we need to show that the size of G is at most Q. Okay, so let G to the K be in G for some K in what is CO to P minus 1. Then there exists H is equal to G to the N such that G to the K is equal to G to the N. Yeah, I should write this L times R mod. So it's mod P minus 1 because we are in the exponent. And in the exponent, things happen mod P minus 1, right? Because the exponent goes from 0 to P minus 1. So, sorry, 0 to P minus 2. Yeah, because the group has size P minus 1, so it goes from 0 to P minus 2. Yeah, so in the exponent, things happen mod P minus 1. So we have that K equals to LR, L times R mod P minus 1, right? Oh, wait, no, I should write it like this. Okay, yeah. So we have that GK is equal to G to the LR mod P. And uh, hence GK is contained in. Okay, so GK is contained in this set. This is exactly equals to Q times. Yeah, it's exactly equals to Q, right? So is this fine? So we showed that this set GR, G to the 2R, to G to the QR, they are distinct and are contained in G, and G is also contained in this, right? So both have to be exactly the same. Yeah, so that's all we have for today. So if there are no other questions, we can meet next week. Okay, yeah. So there are no other questions. Yeah. Thank you.